So again, we're going to have a balanced equation. We're going to convert the mass of each reactant into moles using the molar mass. Once we have the moles of each reactant, we're going to convert them to the moles of product, in this case aluminum sulfide, using the mole ratio. Then we pick which one it produces the fewer moles of product. That's going to determine which reactant is the limiting reactant. And then we're going to take that moles of product, multiply it by the molar mass to get the mass of aluminum sulfide. And again, this is referred to as the theoretical yield of the reaction. And the reason I'm pointing that out is because later on, we're going to be using that term when calculating percent yield. So make sure you remember theoretical yield. So that's how we're going to answer the first part. Now to answer the how much excess reactant is left over, we got to do a slightly different process. We're going to take the mass of product produced by the limiting reagent, converted to moles. It should actually be moles of product. So you take the moles of product produced by the limiting reagent, use the mole ratio, and convert it to moles of the excess reagent. Once you do that, you're going to convert this to mass of excess reagent. And again, this is how much of the excess reagent is used. Once we have that, we can subtract it from the initial amounts and we get the mass of excess reagent left over. So this is the general process we're going to do for this problem and also problems similar to this. So now let's look at the actual calculations. So again, the balanced chemical equation, remember sulfur is octaatomic. It's a 8-membered ring sulfur molecule. So you need a balanced equation so that you can get the mole ratios of each. We're going to first convert mass to moles. So here you notice we start with 10 grams of aluminum. Since we're going from grams to moles, we have to divide by the molar mass of aluminum, and we get moles on top. Then using the mole ratio, here we have 16 moles of aluminum, 8 moles of aluminum sulfide. So again, since aluminum is on the left-hand side, the moles of aluminum go on bottom, and the moles of aluminum sulfide go on top. So that way the moles of aluminum cancel. And now the only thing we have left is the moles of aluminum sulfide. We're going to do the exact same thing with sulfur. Again, we start with the mass of sulfur. We divide it by its molar mass so that the grams cancel out. Now we have moles. Again, from the equation, there's a 3 in front of sulfur, an 8 in front of aluminum sulfide. So this is the ratio of 3 to 8. The moles of sulfur cancel out, and we're left with moles of aluminum sulfide. So you have to do this process for every reactant that's in your equation. This one's 2 reactants, but if it was 3 reactants, you would do the same thing and see how much product is produced by each reactant. So now we see we get the moles of product produced by each reactant. You have to ask yourself the question, which one produces the fewer moles of product? So in this case, it would be sulfur is the one with fewer moles of product. So sulfur is the limiting reactant. And since sulfur is the limiting reactant, we're going to take the moles of product produced by sulfur multiplied by the molar mass to get the mass of aluminum sulfide that is formed. So 23.4 grams of aluminum sulfide. Now again, this is referred to as the theoretical yield. Now that we know that sulfur is the limiting reactant, we can forget everything about aluminum. So don't worry about aluminum now. We don't need anything from it, so just mark it off. So now we need to find the excess reagent. So to find the excess reagent, we're going to take the moles of product produced by the limiting reactant, in this case the 0.156, and we're going to convert it to moles of aluminum. So we're actually back calculating from moles of aluminum sulfide to moles of aluminum. So again, we get the mole ratio from the balanced chemical equation, and then we're going to multiply it by the molar mass of aluminum to get the mass of aluminum that was used. So again, this 8.424 is the mass of aluminum that was used when we added 15 grams of sulfur to it. So now to find the amount that was left over, we take the initial, which is 10, subtract it from the used, which we calculated, and we get there's about 1.58 grams of aluminum left over. So that would be the answer for the second part of the problem. So here we have another limiting reactant problem. We want to know what's the theoretical yield of chromium that can be produced with a reaction of 40 grams of chromium 3 oxide with 10 grams of aluminum, given the chemical equation below. So we have the balanced chemical equation. We want to know how much chromium can be produced when we react these two reactants. So 40 grams of chromium 3 oxide, 10 grams of aluminum. So we're going to be setting up similar calculations for aluminum and chromium 3 oxide. Set up some train tracks. All right. So again, first we're going to start with the mass of aluminum. And we want to convert it to moles, so we're going to have to divide by the molar mass. Remember that aluminum, 27 grams of aluminum equals 1 mole of aluminum. And this comes from the from the periodic table. Since we're starting with grams on the left, it goes on the bottom, and the moles goes on top. Now we have the moles of aluminum. We want to convert it to moles of chromium. So we're going to look at the balanced chemical equation. 2 moles of aluminum gives us 2 moles of chromium. So the mole ratio here is 2 to 2. Set that up. Again, aluminum goes on the bottom because we're starting with aluminum on the top left. And now we can determine the moles of product produced by aluminum. We're going to do the exact same thing again with chromium 3 oxide. We're going to start with the mass of chromium 3 oxide, which is 40 grams. Again, we want to convert that to moles, so we're going to divide by the molar mass. So remember the molar mass, 1 mole of. Gotta look at the periodic table. So again, the 52 and the 16 I've obtained from the periodic table. And the molar mass is 152 grams. So 1 mole of chromium 3 oxide is 152 grams. So we're going to put again the 152 on the bottom because we're starting with mass. So in order to convert the moles, we have to divide by the molar mass. Next, we want to look at the mole ratio. So again, in front of chromium 3 oxide is a 1, in front of chromium is a 2. So the 1 mole, let me write it up here. 1 mole of chromium 3 oxide equals 2 moles of chromium. So this will tell us the amount of product produced by 40 grams of chromium 3 oxide. And we get so now we have the moles of chromium produced by each reactant. And we see here that aluminum produces the fewer moles of product. So aluminum is our limiting reactant. Chromium 3 oxide is the excess reactant. So we can forget everything about chromium 3 oxide. We don't need it anymore. So now we want to convert the moles of chromium produced by the limiting reactant to grams. So we're starting with this many moles of chromium. Now remember, 1 mole of chromium is equal to 52 grams. So since we're starting with moles, in order to convert this to mass, we have to multiply by the molar mass. So the 1 mole of chromium, 52.00 grams of chromium. And we get about 19.2 grams of chromium. Remember, this is referred to as the theoretical yield. Record this. So here again, we have a reaction involving calcium, magnesium 4 nitride. We have 65 grams of calcium, 57 grams of manganese 4 nitride. We want to know what's the theoretical yield of manganese. And it gives us the balanced chemical equation and the molar masses. And to kind of help identify where to put what pieces of information, I've labeled you can call them train tracks in the different sections. So for calcium and magnesium 4 nitride, we have 3 train tracks labeled in 3 sections. And again, I'm going to tell you what goes in each section. And that way it kind of helps you to organize the different pieces of information. So let's start with calcium. Again, it's going to be a duplicate from manganese 3 nitride, but in track 1, if you want to call it, is the mass of reactant. That's what you're always going to put in track 1 when you're given mass of reactant. So let's go ahead and do that. We're going to put the mass of reactant that we were given in the problem. And I'm going to do the same thing with manganese 4 nitride. So again, in slot 1 or track 1, we're going to put the mass of each reactant that was given to us in the problem. In slot 2, is the molar mass of reactant. Remember, molar mass is the mass equal to 1 mole. And so in this slot 2, the mole is going to go on top, the mass is going to go on the bottom. So for slot 2, we're going to put 1 mole on top, and we're going to put the mass of 1 mole on the bottom. And we're going to do the same thing with manganese 4 nitride. Again, the mass of 1 mole goes on the bottom, and the 1 mole goes on top. Now in slot 3 goes the mole ratio. So typically the way the mole ratio is, the product on top, reactant on bottom. This is generally what you do. So you're going to make sure to put the coefficient of the product on top, the coefficient of the reactant on the bottom. So here we do that. For calcium, it's 6 moles of calcium and 3 moles of manganese. And then for the bottom one, 1 mole of manganese 4 nitride, 3 moles of manganese. And just to let you know, for slot 4, we're not going to need it yet, but for slot 4 is the molar mass of product. And so here, for step 4, the mass on top, mole on the bottom. The opposite of step 2. So step 2 and 4 are just opposite. So for manganese, it's 54.9 grams, 1 mole. Now, when we work this out, we get the moles of product produced by each reactant. Now we can identify the limiting reactant. In this example, the limiting reactant is manganese 4 nitride. So now we're going to take the moles of product produced by the limiting reactant and put it right here. And so mass times moles, mass times molar mass times moles gives us the mass. And we get 42.5 grams of manganese. So that would be, again, the theoretical yield of this reaction. So here we're given another chemical reaction. We want to know how much excess reactant is left from the reaction of 20 grams of manganese 4 oxide and 35 grams of HCl. And we're given the balanced chemical equation and the molar masses. And so there are many different ways you can approach this problem. I'm going to approach it one way, but if you approach it another way and you get the same results, no problem, because there's about 2 different ways you can approach this problem. So just to kind of give you an overview of what I'm going to do, I'm going to take the mass of reactant, convert it to moles of reactant. I'm going to convert it to moles of one of the products. It doesn't matter which product, but I'm going to convert it to one of them. I'm going to convert it to moles of chlorine. And again, it doesn't matter which product you choose, as long as you choose one product. And then based on the moles of chlorine, determine the limiting reactant. And then calculate or get the mass of excess reactant that was used, and then excess reactant left over. That's the steps we're going to take in order to determine the excess reactant. So the first three steps, the same steps we've done in the past in the previous problems. So let me throw up some train tracks. So we're going to do one for manganese 4 oxide, the other for HCl. So again, we got slots 1, 2, and 3. Refer to the previous problem, you know what goes in each slot. So slot 1 is the mass of the reactant, so that's 20 grams. Slot 2 is the molar mass, and here, since it's this set of tracks, the mass goes on the bottom, the moles go on top. Remember, slot 2 is the molar mass, mass on the bottom, mole on top, and slot 3 is the mole ratio. Here there's a 1 in front of manganese 4 oxide and a 1 in front of Cl2. So we put the reactant on the bottom, product on top. We do the same thing with HCl. Again, slot 1 is the mass of the reactant. Slot 2 is the molar mass. Again, the mass goes on the bottom. The moles goes on top. And slot 3 is the mole ratio between HCl and Cl2. So in front of HCl is a 4, in front of Cl2 is a 1. So this is 4 moles of HCl. Again, the reactant is on the bottom. The product is on top. Now we need to determine which one produces the fewer moles of product. So in this case, MnO2 produces the fewer moles of product. So MnO2 is our limiting reactant. So now we're going to take the moles of product produced by the limiting reactant and calculate how much excess reactant was used. So let me set this up. Again, we're going to start with 0.230 moles of Cl2. We got to convert this to moles of HCl because HCl is our excess reactant. So again, we're going to use the mole ratio. So 1 mole Cl2, 4 moles HCl. And then we're going to convert that to mass. So since we have moles, the 1 mole goes on the bottom. 36.5 grams on top. This will tell us how much HCl was used. And we get 33.6 grams. And by the way, the amount used should always be less than the initial amount, because again, this is the excess reactant. So the amount in excess or leftover is the initial minus the used. 1.4 grams left over. So that would be how much HCl is left over from this reaction. So here we're given a combustion reaction. It says that 5,300 grams of CO2 are produced when 1,500 grams of butane reacts with 9,500 grams of oxygen gas. Calculate the percent yield. So first off, percent yield is a ratio between the actual and the theoretical. So it's actual over theoretical times 100. So in order to solve for the percent yield, you need the actual yield and the theoretical yield. Now the difference between the two is that the actual yield is given to you somewhere in the problem. And typically it's going to be a product. Well, it should be a product. And so here, if we look, we see that 5,300 grams of CO2 are produced. So this 5,300 grams of CO2 is the actual yield. So the actual yield's already been given to us in this problem. It's 5,300 grams of CO2. So that's one piece of the puzzle. What's missing is the theoretical yield. Because once we know the theoretical yield of CO2, we can calculate the percent yield. Now, if you remember from the previous examples we've done, the theoretical yield is the yield of the product produced by the limiting reactant. So what we need to do now is we need to take the mass of each reactant, convert it to moles, and then convert it to moles of CO2 to see which one produces the fewer moles of CO2. And then from there, we can calculate the theoretical yield of CO2. So again, we're going to be using those numbered slots, 1, 2, and 3. We're going to be doing it twice, one for butane and one for O2. So again, in slot 1 goes the mass of the reactant. So in this case, 1,500 grams of butane. Same thing goes for slot 1 for O2. It's the mass of oxygen gas given to us. Next for slot 2 is the molar mass. And since we're going from mass to moles in the molar mass, the mass goes on the bottom, the 1 mole goes on top. So for butane, it's 58 grams of butane and 1 mole of butane. And for O2, it's again 32 grams O2, 1 mole of O2. That's slot 2. Slot 3 is the mole ratio. So butane to CO2. Butane is 2. CO2 is 8. So again, since we're starting with butane here, butane is going to go on the bottom. CO2 is going to go on top. Same thing with O2. If we look at the mole ratio, 13 moles of O2 produce 8 moles of CO2. So since we're starting with moles of O2 on the top in slot 2, it goes on the bottom in slot 3. Now we're going to see which one produces the fewer moles of CO2. So now we see the moles of CO2 produced by each reactant. So again, in this example, C4H10 is the limiting reactant because it produces a fewer moles of CO2. Just to make a quick note, just because in this example, butane or C4H10 is the limiting reactant doesn't mean if you were to see this equation again with the same reactants but different masses, it may or may not be that C4H10 is the limiting reactant. So it depends on the mass of the reactants given. So now we're ready to convert this to mass. So here we put our moles of CO2 produced by the limiting reactant. In slot 4 is the molar mass of the product. Here the mass goes on top and the moles go on the bottom. This is going to tell us the theoretical yield. We get about 4,550 grams of CO2. So here when we calculate the percent yield, we'll notice that there's some error in the way the actual yield was obtained, because for percent yield it should never be over 100. If it's over 100, what that means is that there's some serious problem with the reaction. So here you see that it's over 100, which would indicate to the person doing the experiment that they should go back and recheck or redo the experiment. So this would be 116% yield. So again, if you were doing an experiment and you got a percent yield over 100, that's a bad thing. So somewhere maybe you didn't dry your sample, or there was some impurity that was collected with this CO2. Less than 100 is okay. Greater than 100, not okay. So again, as we're doing these examples, hopefully you're seeing the trends in the process that is needed to solve these problems. We're doing the exact same thing every time. So here we have a precipitation reaction, just one small technical issue here. This should be a solid, not an aqueous. And so we have a precipitation reaction between sodium phosphide and tin-4 nitrite. We produce sodium nitrite and tin-4 phosphide. We use 225 grams of the sodium phosphide, 450 grams of tin-4 nitrite to produce 175 grams of tin-4 phosphide. What is the percent yield of tin-4 phosphide? Again, percent yield is the actual or theoretical times 100. And so from the problem, either directly or indirectly, it's going to give you the information about the actual yield. So here, if we read this problem, we see here that it says to produce 175 grams of tin-4 phosphide. So this 175 grams is the actual yield. So that's something we know. But it's the theoretical yield that we don't know, and we have to use the other information to determine it. So since it gives us information about both reactants, now if it just gave us information about one reactant, it's very easy because that one reactant would be the limiting reactant. But since it gives us information about both reactants, we have to determine which one produces the fewer moles of tin-4 phosphide, and then from there we can calculate the theoretical yield. So again, just like in the previous examples, I'm going to set up my train tracks for both sodium phosphide and tin-4 nitrite. And again, the slots 1, 2, and 3. And 4. So again, in slot 1, what goes there? That's the mass of the reactant, which is given to us in the problem. In slot 2, that's the molar mass of the reactant with the mass of the bottom, the moles on top. The same for tin-4 nitrite. And then 1 mole on top. And you're seeing the same setup. For the row 3 is the mole ratio. So 1 mole of sodium phosphide produces 1 mole of 10,4 phosphide. Now I forgot to check, it wasn't balanced. So to balance it, we need a, excuse me, that's good, I checked. Always check. We need a 4 there and a 3 here and a 12 here. Now we have a balanced chemical equation. About made a boo-boo right there. So now we look here. We got 4 moles of sodium phosphide produces 1 mole of 10,4 phosphide. So again, since we're starting with sodium phosphide, it goes on the bottom, and 10,4 phosphide goes on top. With 10,4 nitrite, excuse me, we have 3 to 1. So again, the 3 is going to go on the bottom because we're starting with 10,4 nitrite. And 1 mole of 10,4 phosphide goes on top. Now in slot 4 over here, this is the mass of the product we're interested in. So since it's 10,4 phosphide, the grams are going to go on top. The mole is going to go on the bottom. Now we need to see which one produces the fewer moles of product. So here we notice that in this example, 10,4 nitrite is the limiting reactant. So we don't have to worry about anything about sodium phosphide. So now we're going to take the moles of 10,4 phosphide that were produced by the limiting reactant and convert that to mass. And again, this is going to tell us the theoretical yield. So again, this is the theoretical yield. So now we have the theoretical yield, the actual yield. We can calculate the percent yield. And we get 73.5%. So this percent yield is fairly good. I mean, depending on what type of reaction you're doing. If it's a well-known reaction, you'd want a percent yield, between 80 to 100%. If you're trying to create or make your own new type of synthesis or reaction, anywhere from 40 to % or up could be good. So it just depends on what type of chemical reaction you're doing to gauge whether or not your percent yield is good or not. But if you're taking a lab, in labs, those reactions are fairly straightforward, so you should get a fairly high percent yield. So this is kind of a different twist to the usual percent yield problems. Here we have a synthesis reaction involving phosphorus and iodine to give us phosphorus triiodide. We have 27 grams of phosphorus, 68 grams of I2. This reaction has a percent yield of 60%. What is the actual yield of the reaction? So sometimes when you look up reactions, if they're fairly, they're well known, they're reported in literature, they say, hey, this reaction has about a 60, 70% yield. What's the actual yield you can obtain if you use this much reactant? So here what we're looking for is the actual yield of the reaction. So remember, from percent yield is the actual or theoretical times 100. So to calculate the actual yield, we need to know the percent yield, which we do at 60%. And we need to know the theoretical yield, which we don't know. So we have to use the other information given to us to calculate the theoretical yield. So again, we're going to set up our train tracks. One for phosphorus, one for iodine, then of course this train track over here. So again, in slot 1 is probably like a broken record by now, but slot 1 is the mass of each reactant. 27 grams of phosphorus, 68 grams of I2. Slot 2 is the molar mass of phosphorus, 24 grams. The molar mass of I2, 254. So again, in slot 2, the mass of the molar mass goes on the bottom. The moles goes on top. For iodine, the mass of iodine in 1 mole goes on the bottom. The moles goes on top. Slot 3, that's the mole ratio between the reactant and the product. So for phosphorus, 1 mole of phosphorus gives us 4 moles of product. So since we're starting with phosphorus, it goes on the bottom, and phosphorus triiodide goes on top. Do the same thing with I2. I2, 6 moles of iodine give us 4 moles of phosphorus triiodide. So again, since we're starting with iodine, iodine goes on the bottom. Phosphorus triiodide goes on top. Now we see which one produces the fewer moles of product. So here we notice that I2 is the limiting reactant. And so we can disregard everything about phosphorus. Now we're going to take the moles of product produced by the limiting reactant and convert it to grams. So again, here goes the moles. In slot 4 is the molar mass of PI3. So 1 mole PI3 equals 412 grams. So now since we're converting to mass, from the molar mass, the mole goes on the bottom. The mass goes on top. Get 73.3 grams PI3. So again, this is a theoretical yield. Now to calculate actual yield, is equal to the percent yield divided by 100 times the actual, theoretical yield. And we get approximately 44 grams of PI3. So if we were to do this reaction, the best we can get 60% yield, so we use 27 grams of phosphorus, 68 grams of I2. The best we can get as far as actual yield would be 44 grams. So again, this is another twist on how you could be presented with a percent yield problem.